Hello, myself Naveen, and today we are going to discuss JEE practice set of electromagnetic induction and alternating currents. Okay. So let's start from the first question. First question is, according to Faraday's law of induction, first one, an electric field is produced by time-varying magnetic field. Second, a magnetic field is produced by time-varying electric flux. A magnetic field is associated with a moving charge and none of it. So if we'll recall Faraday's law of induction, then it states that EMF induced is equals to rate of change of flux. Okay, d phi over dt, where flux depends on magnetic field. So here we can say that if there is a time-varying magnetic field, then there will be an induced electric flux. So option A is right in this question. Second question is, Lenz's law is consequence of law of the conservation of. So Lenz's law states that any induced quantity always opposes the main reason behind its induction. Okay. So ultimately it supports the concept of conservation of energy. So option D is correct in this question. Next question is, a magnet is moving towards a coil along its axis and EMF induced in the coil is E. Okay, so there is a coil. We can take it as a coil and a magnetic pole is moving towards it. Let's suppose north pole is moving towards this coil, and due to that there is induced EMF E. If coil also starts moving towards magnet with same velocity, with same speed, okay, then what will be the induced EMF? So we must take care that induced EMF is always depend on time varying magnetic field, and if we'll talk about the magnitude, so it is proportional to relative motion between field magnet and coil. Okay. So here you can see this both are moving in opposite direction. So relative velocity is 2v. Okay. So if initial case when coil was at rest, then EMF induced is E. Now relative velocity is twice, so net EMF induced in this case would be 2E. Now let's see next question. In this case it is saying an electric potential difference will be induced between the ends of the conductors shown in figure when it moves in the direction. So here you can see a conductor is placed in between magnetic poles. So magnetic field would be generated from north pole to south pole, and for the induction of EMF there must be change in magnetic field. Okay, so this entire field is passing through the cross section of this region. Here you can see. So we need to move this conductor in such a way so that net flux passing through it should change. Okay, so if we'll move this conductor in direction of M, okay, so area interfacing the coil would change. Okay. And if area is changing, although your magnetic field is constant, but net flux will be changed according to time or depending on time, because phi equals to V into E. So it means if we'll move our conductor along direction of M, then there will be change in flux and we'll get a resultant potential difference. On the other hand, here you can see if we'll move along L or along Q, there will be no change in flux because the entire field is passing through its region and there is no change in area. Okay. So for this question, option D is right. Now next is a coil having 500 square loops. So total number of turns are given, that is 500. Okay, and each side is 10 centimeter. So it means it's a square loop and each side is 10 centimeters. So we can calculate its area. Area is 10 centimeter into 10 centimeters, so it is 100 centimeter square, and we can convert this in meters. So it is 100 into 10 to power minus 4 meter square. Okay, and placed in the magnetic field in which your field is increasing with the rate 1 Tesla second. So your V is changing with 1 Tesla per second. It is rate. Okay. So from here we can see that induced EMF is equals to delta phi over delta t. Okay. And delta phi is, if B is changing, then we can say it is delta B into A over delta t. Delta B is 1. One second. Delta B is 1. A is 0.001, and this is divided by multiplied by n, because we have to calculate total flux, and total flux is, let me correct this formula, this is n delta phi over t. So we have to multiply it by 500. Okay, so net induced EMF will be 0.5 volt. I think it is right, it will perform correct calculation. This is 0.001 multiplied by 500, okay, to 1. So it is, okay, this is 0.01. Here I am committing a mistake because it was 10 to power minus 4. So 0.01 multiplied by 5. So correct answer is 5 volt. Now next question is, a current coil changes its current from 0 to 2 ampere in 0.5 second. If induced EMF is 80 volt, then find the self-inductance of the coil. So we will write the formula for induced EMF with respect to inductance of coil. So it is L delta I over delta T. Okay. Because it is for AC, it is E equals to L di over dt. So here we are writing delta I over delta T. Okay. So E is given 80 volt. We have to calculate L. Delta I is current is changing from 0 to 2, so it is 2 ampere, 0 minus 2 minus 0, and time is 0.5. So L is equals to, we need to divide by 2, so 40 multiplied by 0.05. Okay, so it is 2. So the inductance of coil is 2 Henry in this case. Let's see next question. It is saying two inductors, each of inductance L, are connected in parallel, okay, but are well separated from each other. Then the effective inductance. So here we have parallel combination of two inductors. So because in this case division of current would take place just like resistance, okay, although voltage will remain same across it, or we can derive in terms of flux, but here I am writing the direct formula as this is 1 over L1 plus 1 over L2, or we can say it is L equals to L1 L2 over L1 plus L2, although both numeric value are same, value of L1 and L2. So from here we'll get L over 2. So net inductance is L over 2 for question number 7. Let's see next one. It is saying when current I, a direct current I passes through an inductor of inductance L, then energy is stored. Okay. So we all know that energy is equivalent to work done if we can calculate the work done. So we can write that work done is equals to power into dt. And in terms of EMF and current, power can be written as E into I into dt. Okay, and EMF can be written as L minus L di over dt, but here we are taking the magnitude, so EMF is L di over dt. So net work done in terms of magnitude is equals to energy stored. It will integrate this, and that is equals to integration of dt and dt will be cancelled if we will substitute EMF is equals to L di over dt. So from here we'll get L I into di, current changing from 0 to I we can take. So this is half Li square. So right option is option number C. Let's see next question. It is saying an EMF of 5 volt is induced in an inductance when current is changing from 3 to 2 ampere in 1 millisecond. Then inductance. So we already solved one question similar to this, that EMF is equals to, in magnitude of, it is L di over dt, or for this case we can write delta I over delta t. Okay, so L is equals to EMF, that is 5, into change in time, that is 1 millisecond, so we can write 1 into 10 to power minus 3, and divide, current is changing from 3 to 2, so change in magnitude is 1. 3 minus 2 is equals to 1. Okay, so from here we'll get L equals to 5 into 10 to power 3, so this is 5 millihenry. So option A is right for question number 9. Next is dimensional formula of self-inductance. Okay, so there are many ways to calculate the dimensional formula. Let's find out easiest way. That we know what is potential. Electric potential in magnitude is product of electric field and distance. Okay, and electric field is force per unit charge into the distance. Okay, and we are familiar with dimension of force, that is MLT minus 2. And dimension for length is L, and charge can be written as I into T. So dimension of current is A, and another one is time. Okay. So from here we'll get dimension of voltage or EMF is M L square A to power minus 1 into T to power minus 3. Okay. Now we know that EMF or voltage is equals to L delta I over delta T. So from here we can find out dimension of L, that is self-inductance. We already have dimension of voltage, that is ML square A to power minus 1 into t to power minus 3 into, if we'll just do mathematical manipulation, so it is t and dimension for current is a in denominator. So final dimension for inductance would be m L square a to power minus 2 and t to power minus 2. Okay, so this is option number C. So option C is right here in question number 10. Now next question is, a copper ring is held horizontally and a bar magnet is dropped through the ring with its length along the axis of ring. So there is a ring placed on horizontal surface and a magnet is falling from certain height. Okay. Now the acceleration of falling magnet is, options are, it is equal to the gravity, it is less than the gravity, more than that due to gravity, depends on diameter of the ring and length of the magnet. Okay. So here we need to recall the Lenz law, because when a magnet is dropping down, okay, over the ring, so there will be change in flux passing through this magnet. Okay, so if there is change in flux passing through the magnet, passing through this coil, then there will be an induced current. Okay, and according to Lenz law, it will develop a polarity that will oppose this motion. Okay, so apart from gravitational force mg, there will be a repelling force due to polarity developed in this coil because of induced current. So this particular force, let's consider this force is Fm. So this magnetic force will reduce the net magnitude of force working on this magnet. And if your net magnitude is less, then definitely acceleration would be something less than acceleration due to gravity. Okay, so option B is right in this question. Okay, now next question is quite similar to previous one, but there is a very small modification, that a copper ring having a cut such as not to form a complete loop, and rest of the conditions are same. Okay, so if there is a coil with a cut and we are dropping a magnet from certain height, so again there is change in magnetic flux passing through it, but this cross section is not complete. Okay, so there will be no induced current. Okay, if there is no induced current, so there will be no opposite polarity. Okay, and the only force working on this magnet would be its gravitational weight. Okay, so in this case it will experience an acceleration, that is acceleration due to gravity. Okay, so option A is correct for question number 12. Okay. Now question number 13, there are two circular loops P and Q are placed with their planes parallel to each other. A current is flowing through P. If this current is increased, then the loop will attract each other, the loop will repel each other, the loop will neither attract nor repel, and the loop Q will start rotating. So we need to look at the fundamental process in this case. Now if you hold this conductor in your right hand and look at the field induced by this conductor, so the direction of magnetic field due to this loop P will be in rightward direction. Okay. Now as current is passing through changing in coil P, so there will be a variable magnetic field basically directed rightward in coil 2. Okay. And if magnetic field is variable, then it will leads to change in flux, because flux is dependent on magnetic field. And if there is change in flux passing through a coil, so there will be induced EMF. Okay. And again a current will be generated in coil number Q. Okay. And the direction of current would be like this, because it will oppose the main phenomena. And in result of that, there will be opposite magnetic field according to Lenz. B dash we can consider. Okay. And due to that, there will be a repulsive force. So the loops will repel each other when we are increasing current in loop P. Okay. So option B is correct in this case. Now let's see next question, question number 15. It is saying a rectangular coil having 100 turn, size 0.1 meter, 0.05 meter, placed perpendicular to a magnetic field near to a field 0.1 Tesla. If field drops from 0.0 drops to 0.05 in 0.5 second, then find out induced EMF. So again it is given number of turn, that is 100. There is change in magnetic field, so we can find out delta B. It is 1 minus 0.1 minus, in fact 0.05. Okay, so net change is 0.05 Tesla, and duration is given for this change is 0.05 second. Area is also given. Area is 0.1 into 0.05. 0.1 into 0.05. So this is 0.1 second. There is some technical glitch, so let me write it again. This is 0.005 meter square. Okay. So we have change in magnetic field, so we can calculate change in total flux delta phi, that is N delta B. Okay. So it is 100 into 0.05. So let's write it as such. We'll perform final calculation later on. And change in flux is delta phi over induced EMF is equals to net change in flux, that is N into delta phi over delta T. Okay, and this delta phi is N into B into area of this. So area is already we calculated that 0.005 meter square. Okay, so for induced EMF we need to divide this quantity by change in time, that is 0.05. So these two quantities will get cancelled out and will get 0.5 volts. So correct answer is option number A. Let's see next question, question number 15. A wire of length 1 meter moves with a speed v 10 meter per second perpendicular to a magnetic field. If EMF induced is 1 volt, what is the magnitude of magnetic field? Okay, so it is a problem of motional EMF. Okay, that if there is a frame and it is placed in a magnetic field, like this, okay, and a wire of length L is moving with certain velocity v. Then by applying simple concept of induced EMF and change in flux is equals to E equals to B into V into L, which is called motional EMF. Okay. So in this question, EMF is given, velocity is given, and length is given. Okay. So we can calculate magnetic field. So magnetic field is EMF divided by voltage into velocity into length. EMF is 1 volt, okay, velocity is 10 meter per second, and length is 1 meter. So magnetic field of this region would be 0.1 Tesla. So correct answer is option number B. Let's see next question. It is saying the wings of an aeroplane are 10 meter apart. So again we can take this length, the distance between two wings is 10 meter, okay, and the plane is moving horizontally towards the north with velocity 200 meter per second. So V is given, that is 200 meter per second. And the component of Earth's magnetic field, which is perpendicular to the horizon, is 0.5 into 10 to power minus 4 Tesla. Okay. So the induced EMF set between the tips of the wing. Again, it is based on motional EMF, where E is equals to B into V into L. Okay, so all these quantities are given. So this is V into V. V into L is 2000, and this is 0.5 into 10 to power minus 4. Okay. So it will multiply it, will get 1000 into 10 to power minus 4, so that is 0.1 volt. So correct answer is 0.1 volt, option number A. Let's see next question. It is saying a coil of cross section 400 centimeter square having 30 turns, and it is making a revolution 1800 revolution per minute in a magnetic field of 1 Tesla. So the peak value of EMF induced. So look, when we write expression for flux whenever rotation is taking place, if at any particular instant the angle between coil area and direction of magnetic field is phi, like this is area of coil and this is your magnetic field, is that this angle is theta, and if it is rotating with speed omega, then theta can be written as omega t. So it is NAB into cos omega t. Okay. Now we will apply the concept of induced EMF, that is E equals to minus d phi over dt according to Faraday's law. Then we'll get expression for EMF is equals to NAB into omega into sine omega t. Okay, so now in this case it is asking for the maximum peak value of induced EMF, and we already know that the maximum value of sine omega t is 1 because it's a trigonometric function that attains maximum value between plus 1 and minus 1. So the peak value of EMF is NAB omega. Okay. And all these parameters are given, but please keep in mind that we need to convert this revolution per minute into revolution per second. Okay. So, and for omega, we have to find out radian per second, and omega is equals to 2 pi f. Okay. So, n is 30. Area is 400 centimeter square, so we can write 400 into 10 to power minus 4 SI unit. Magnetic field is 1 Tesla, and this omega is 1800 divided by 60. This is our frequency, revolution per second, into 2 into pi. Here you can substitute pi equals to 3.14. Okay, so it will calculate this, will get 226.2 volt approximately. So correct answer is 226 volt. Now next question is, a conducting square loop of side L and resistance R moves in its plane with uniform velocity that is perpendicular to magnetic field is B. This B is constant in time and space, pointing perpendicular into the plane, and this loop exists everywhere. So what is the current induced in this loop? Now see, this is very interesting case. Whenever there is induced EMF, then the primary requirement for that there must be a time varying flux which is changing with time. Okay. But in this case, as this entire area lies in between a constant magnetic field, so B is constant, area is constant, so this flux will remain constant. Okay. So this loop will experience induced EMF if it enters from any outer region or if it gets out from this region. Then definitely there will be change in area which exists inside the magnetic field. Then we'll get induced EMF. But in present case, the entire loop exists inside a constant magnetic field, so there will be a constant flux. Okay, and if there is no change in flux, then there will be no induction. So net induced EMF is equals to 0 in this case. Now next question is, a rectangular coil of single turn having area A rotates in uniform magnetic field B with an angular velocity omega about its axis perpendicular to the field. Okay. If initially the plane of the coil is perpendicular to the field, then what is the average EMF induced when it has to rotate through 90 degrees? Okay. So EMF induced is, again we are going to use Faraday's law, that is delta phi over delta t with negative sign, but here we are focused on magnitude. So it is B into A upon T. Okay. But here time is not given. Okay, but when coil rotates through 90 degrees, then angular displacement is pi by 2. Okay, and omega is given as angular velocity is given as omega. So we can calculate T, because omega T is equals to angular displacement. So this is pi by 2 omega. Okay. Now if we'll substitute in this equation, then EMF is equals to B into A upon pi by 2 omega. Okay, so E is equals to 2 omega B A over pi. So right option is option number D. Let's see next question. It is saying, a coil is rotate uniform magnetic field about its axis that is perpendicular to the field. the EMF induced in a coil would be maximum when the plane of coil is. Okay, so look, again we need to recall that concept what we discussed in question number 17, that the EMF expression of EMF induced can be written as NB omega A into sine omega t. Now this omega t is angle between areal vector of the coil, okay, and the magnetic field. This is areal vector, and this is magnetic field. Okay. This angle is omega t. Now this magnitude of EB will be maximum when omega t is equals to 90. Okay, so the area vector of coil will make 90 with the magnetic 90 angle with the magnetic field if it lies in parallel to the magnetic field, because area vector is always perpendicular to the surface. Okay. So correct answer is parallel to the field. That whenever this coil is parallel to the field, there will be 90 angle between magnetic field and area vector, and from there we'll get maximum EMF. Now next question number 21. Now next is the mutual inductance of pair of coil each of turn N is M Henry. If a current I ampere in one coil brought to 0 in t seconds, then average EMF induced in other coil. Okay, so EMF induced in other coil due to mutual inductance can be represented as E equals to number of turn and mutual inductance into Ti over Dt. Okay, because it is the rate of change of flux. So from here we can write that E equals to N into M into I upon T, right? Because current I changes from 0 to I, it is current is changing in time T. Okay, so we can replace delta I by I and delta T by T. Okay, we are taking average value. So net induced EMF is NMI over T, but it is asking for the average induced EMF in other coil. In other coil there is also n number of turn. So if you calculate EMF induced per unit turn or average EMF, then we need to divide it by n and we'll get EMF induced per unit turn is equals to Mi over T, where M is mutual inductance, I is change in current, and T is time duration required for that change. So option A is right. Let's see next question. It is saying if L and R denotes the inductance and the resistance, then the dimension of L over R. Okay, so in one of the previous question we already calculated dimension of L. Okay, the procedure is same, that you can calculate dimension of voltage, then use relation between voltage and inductance, and we'll get M L square A to power minus 2, okay, and T to power minus 2 for inductance. Okay. On the other hand, if we'll calculate for the resistance, then resistance is equals to V upon I according to Ohm's law. Okay, and we can again get back to the voltage. That exactly don't remember to me that voltage is equals to E into D. Okay, and E is force upon charge. force per unit charge into D. Okay. So force is M L T minus 2 into D, so we can make it L square upon Q. Q is I into T. Okay. So net dimension for the voltage is M L square T to power minus 3 into A to power minus 1. Okay. And for resistance, we need to divide it by current. So we'll get M L square T to power minus 3 into A to power minus. Here we need to find out dimension for L over R. Okay. So dimension for L over R we want to calculate here. So dimension of L is M L square T to power minus 2 and A to power minus 2. Okay. And dimension of resistance is M L square T to power minus 3 and A to power minus 2. Okay, so all respective terms will get cancelled out. This T will move in numerator and will get M to power 0, L to power 0 and T. So option B is right for this question. Next question is Faraday's law of electromagnetic induction is related to. So again, Faraday's law of electromagnetic induction is if there is change in flux, okay, so there will be an induced EMF, and according to Lenz's law, that result of that EMF will try to oppose this change. Okay, it means it is ultimately trying to conserve the entire energy in the system. Okay, so this law also supports the conservation of energy. So option B is correct for question number 23. Next question is the induced EMF of a coil is proportional to. Okay, so look, if we'll try to find out the induced EMF of a coil, so we already know that EMF is related to flux, that is phi total. Phi total is L into I, okay, where L is inductance and I is current. Okay. And we know about the EMF induced, that EMF is minus N delta phi over delta T. Okay, delta phi is N into area into magnetic field divided by delta T. Okay, and we already know that B in any coil is equals to mu N I over L, that is length of the coil. Okay. So from here EMF induced in this coil will be mu N square I into area upon delta L. Okay. So and EMF is L delta I over delta T, into delta T is also there. L delta I over delta T. Okay. So if we'll compare from there, then we'll get expression for mutual inductance or self-inductance of a coil. That is mu N square A upon L. So from this expression it is clear that it is proportional to square of the number of turn, okay, inversely proportional to its length, okay, and directly proportional to its cross-sectional area. Okay, but in this option only favorable option is the square of the number of turn. So L is proportional to N square. Let's see next question. Question 25 is, a coil of area 80 centimeter square, number of turn is 50, it is rotating with 20 revolution per minute about an axis that is perpendicular to a magnetic field 0.5 Tesla, 0.05 Tesla. So again, maximum value of EMF induced, we already derived that formula, that maximum value of EMF is N A B into omega, and all quantities are known here. Here we need to take care that options are given in pi, so we no need to substitute value of pi here. Okay, so N is 50. Okay, area is 80 centimeter square, so it is 80 into 10 to power minus 4. Magnetic field is 0.05, and we have to calculate revolution per second. So this is 2000 upon 60 multiplied by 2 pi for omega. Okay, so we can cancel terms here which are available, and if you simplify this, then you will get 4 pi over 3 volt. Okay, just after solving this part. So option C is right here in this case. Next question number 26, that an EMF of 5 millivolt is induced in a coil when in a nearby placed coil the current changes by 5 ampere in 0.1 second. So find the mutual inductance between two coils. Okay, so delta I is given, that is 5 milliampere. So 5 into 10 to power, 5 amperes. So no need to change it. And T is given 0.1 second. So delta T is 0.1 second. And induced EMF is given, that is 5 millivolt. So this is 5 into 10 to power minus 3. And here we need to calculate mutual inductance. Okay, so we can write that induced EMF in second coil is equals to mutual inductance into delta I over delta T. It is well known relation. So from here we can calculate M is equals to E into delta T over delta I. Okay, so this is 5 into 10 to power minus 3. I is, okay, delta T is 0.1 and I is 5. Okay, so this two term will get cancelled. Okay, and we'll get 0.1 into 10 to power minus 3. So this is 0.1 millihenry. So choice C is correct in this question. Now next one is, a coil of area 0.5 meter square is situated in a uniform magnetic field that is 4 Weber per meter square, makes an angle of 60 degree with respect to magnetic field as shown. Then what is the value of magnetic flux? So this is a direct question. We already know that flux is dot product of magnetic field and area of the coil. Okay, so we will open this relation by simple formula of dot product. This is BA cos theta, where theta is angle between these two quantities. So B is 4, and area is 0.5, and cos 60, we already know that cos 60 is 1 by 2. Okay, so we'll get 1 Weber. So choice B is correct in this question. Next one is, two rails of a railway track insulated from each other and the ground are connected to a millivolt meter. What is the reading of millivolt meter when a train at speed 20 meter per second? So V is given, that is 20 meter per second, okay, along the track. And okay, and the Earth's magnetic field is given, that is P is equals to 0.2 into 10 to power minus 4 Weber per meter square. Okay, and the rails are separated by 1 meter. So again, this is a phenomena where a conductor is moving in a magnetic field, and due to motion of that conductor, which is moving through the magnetic field, there will be an induced EMF, and we already know the relation for induced EMF, that is B into V into L. So we can just substitute all known quantities, 20 into 0.2 into 10 to power minus 4. So from here we'll get 4 into 10 to power minus 4 volt, or we can convert this unit, so it is 0.4 millivolt. So option B is right for question number 28. Next is, a circular loop of radius r is made up of a single turn of thin conductor. The self-inductance is L. If the number of turn in the loop increase to 8, then the self-inductance would be. Okay. So if we'll just recall the previous question, that is question number 20, I think, previous question, not exactly remember, where we just calculated that expression for L, and from there we have got that L is proportional to N square. Okay, so we can say that L dash upon L, where L is original inductance and L dash is new inductance, that is N dash square upon N square. Okay. So new number of turn is 8, so it is 8 square. At initial stage number of turn was 1. So from there we'll get L equals to 64. So if you increase number of turns 8 times, or make 1 turn to 8 turns, then its inductance would be 64 times greater. Next question is, when the number of turn and the length of a solenoid are doubled, keeping the area of cross section is same, then inductance is. Okay, so it is also based on similar formula like previous question. So here let me write the complete formula, that is mu N square A over L. Now in this case it is saying that number of turn is doubled and length is also doubled, keeping area constant. So if number of turn is doubled, then 2n whole square, then it would be 4n square into A, right? Because n dash is equals to 2n as per the question. Okay, and new length is also twice of previous one, so this is 2l. So from here we'll get 2 mu n square A over L. So in this case, this is equals to previous inductance. So inductance is, new inductance is 2L. So you can say that inductance is doubled. So option C is correct. Okay. Next question number 31. It is saying a rectangular coil placed in a region of having a uniform magnetic field B perpendicular to the plane of coil. An EMF will be induced in the coil if magnetic field is increased uniformly, magnetic field is switched off, coil rotate about x-axis, and coil rotate about axis perpendicular to the plane of coil and passing through it from the center. Okay. So in this question we can see that how EMF is induced in this case. Okay. So we already know that EMF induced in a coil depend on rate of change of flux. Okay. So there must be change in flux for the induction of magnetic field. Okay. So let's look at the options one by one. If your magnetic field increased uniformly, then definitely the flux passing through this coil will increase with respect to time. So there will be an induced EMF. So this option is right. Second, the magnetic field is switched off. So again, if magnetic field is reducing to any value 0, then there is change in magnetic field. So again, there will be change in flux, so induced EMF will be there. And if this coil rotates, okay, so the angle between field vector and area vector of this coil will change. Okay, that will leads to change in flux, that if coil rotates with angular speed omega, then you can write expression for flux is phi equals to B into A into cos omega t. Okay, so again there will be a change in flux, so it will leads to induced EMF. Fourth case, coil is rotating about an axis passing through this point and in this plane. Okay. So if coil is rotating in same plane and same magnetic field is passing through it, so there will be no change in flux. So it will not induce any EMF. So for question number 31, three options are correct. Option A, B and C. Now let's see next question. That in this figure, the flux through the loop perpendicular to the plane of the coil as directed into the paper is varying according to the relation 6t square 7t plus 1 and phi in millivevers. T is in seconds. The magnitude of EMF induced at t equals to 2. So first let's calculate the flux, then we'll discuss the remaining part. So induced EMF is the rate of change of flux. Okay. Here we are talking about magnitude, so we don't take the negative sign. Okay. So this is d phi over dt. If we'll differentiate this expression with respect to time, then we'll get 12t plus 7. Okay. 1 is constant, so its differentiation would be 0. Now we have to calculate this EMF at time t equals to 2. Okay. So 12 into 2 plus 7. So net induced EMF is 31 millivolt. Okay. So one thing is sure, that what is the magnitude is 31. Now next is the direction of induced current through the resistance which is connected externally in this coil. Okay. So look, there are two possibilities. Either current will move from left to right, or it moves from right to left. Now if we assume the direction of current from right to left, okay, and you hold this conductor in your right hand and look at the direction of curl, okay. So this direction of curl shows that there is a induced magnetic field which will go in same direction, okay, and it is violation of Lenz's law. Okay. So it means the direction of current is not from right to left. Okay. Now we'll consider that direction of current from left to right. Okay. So if your current is going from left to right, means in this direction, so it would be the direction of current. Again, if you hold the conductor, then you can see that your thumb fingers inside the coil are coming out of the page. Okay, so it means we'll get a magnetic field in opposite direction. Okay, and it supports the Lenz law that every induced quantity always opposes the region behind its induction. Okay, so the new field must oppose the priorly existing field, so that the direction of current should be from left to right, and magnitude we already calculated, that this magnitude is 31 millivolt. Okay, so option D is correct for this question. Now let's see next question. In question number 33, it is saying a 2 ampere current is flowing through a coil of 100 turns that gives rise to a magnetic flux from 5 into 10 to power minus 5 Weber. Okay. So look, what is the magnetic energy associated with the coil? So the expression for magnetic energy we already derived in previous questions, that is half L into I square. Okay, and if there are n number of turns, then we can replace L into I is equals to total flux. Total flux is n into delta phi, but it's changing flux. Okay. So we can rewrite this expression as 1 by 2 into n into delta phi, okay, into I. Okay, so all these values are known, so this is 1 over 2 multiplied by 100 turns are there, so 100, flux is 5 into 10 to power minus 5, and current is 2 ampere. Okay, so this 2 and 2 will get cancelled out. This is 500 into 10 to power minus 5. Okay, so this is 5 into 10 to power 500 into 10 to power minus 5 means 5 into 10 to power minus 3 joule. Okay, so if we'll adjust this numeric value, then we'll get 0.005 joules. So option D is correct for question number 33. Okay. Now next question is question number 34. In this figure, there are two resistance, 10 ohm and 20 ohm are connected, and resistance of 10 ohm is parallel to an inductor of 10 Henry. Now, question is saying if switch is closed at t equals to 0, then what is the initial and what is the final current in this circuit? Okay. So there are number of methods for solving this problem, but at J level we just need to understand few basic fundamentals, that whenever we just connect an inductor to a power supply, then immediately charging does not start. Okay. So when your inductor does not start charging immediately, then net current passing through that inductor is equals to 0. Okay. If net current passing through that inductor is 0, then initially it behaves like open circuit. So you just need to remember this fundamental, that when switch is just on, okay, so even you can make a notation that if we'll write t equals to 0 plus, it means the point when switch is just on, okay, then your inductor charging will not start immediately. So net current in inductor is 0. So inductor will behave like open circuit. Okay. And when you close it for very long time, okay, so inductor is fully charged on DC. Okay. And it is not getting a path of discharging. So it will just pass the entire current through it without any drop. Okay. So it behaves like short circuit. So whenever you get any problem related to switching action, then just remember this thing, that at initial stage replace your inductor with open circuit, and at final stage replace it by short circuit. So we can draw equivalent circuit for time t equals to 0. So at time t equals to 0, this inductor will be open circuited. So in this circuit there will be two resistance, one is 10 ohm, another is 20 ohm. So net resistance is 30 and supply is 2 volt. So current at initially will be 2 divided by 30, that is 1 upon 15 ampere, right? I hope I am not going too fast, that I equals to V over R and V is 2 volt, okay, and net resistance is 30. So we'll get 1 upon 15 ampere. In second case, when your inductor is short circuited for very long time, then if it is in short circuit, then for a parallel combination we already know that R1 R2 over R1 plus R2 is the net resistance. And if one element is short circuited, it means its resistance is 0. Okay, so net resistance will be 0. So for short circuit case, the net resistance of this segment is equals to 0. Or you can remember one thing, that current always follows the lowest resistive path. So whenever you connect any short circuit in parallel to any resistance, then the net value will be equals to 0. Okay. So in this case there will be only resistance active, that is of 20 ohm at t equals to infinite, and net voltage is 2 volt. So current I is equals to 2 upon 20. So net current is 1 upon 10. So correct answer is 1 upon 15 for t equals to 0 and 1 upon 10 for t equals to infinite. Okay. Next question is, two different coils having self-inductance L1 equals to 8 millihenry and L2 is 2 millihenry. The current in one coil is increased at constant rate. The current in second coil is also increased at the same constant rate. At a certain instant of time, the power given to the coil is same. At that time, the current induced voltage and the energy stored in coil are I1 V1 W1 and I2 V2 W. So we have to find out which relation are true. Okay. So we already know that E equals to L into di over dt. This is very first relation. Okay. Now question is saying that the current increased at constant rate. So di over dt is same for both the inductors. Okay. So E1 over E2 from this equation we can write is equals to L1 over L2. Okay. So if E1 over E2 is equals to L1 over L2, so L1 is 8 and L2 is 2. So the ratio for induced EMF is 4:1. Okay. Now second question is saying that power is supplied at constant rate. Okay. So if power supplied at constant rate, then we already know that power is equals to E into I. Okay. So we can say that E1 I1 is equals to E2 I2. Okay. Because power is EMF multiplied by current. So from here we'll get I1 over I2 is equals to E2 over E1, and we already know what is E1 over E2, 4 over 1. So E2 over E1 is 1 over 4. Okay. Next, about the wattage power. So power is, or energy stored, it is saying W is energy stored. Yes, it is not power. So energy stored is half Li square. Okay. So if we'll take the ratio W1 upon W2, that is energy in first coil to the energy in second coil. 1 by 2 and 1 by 2 will be cancelled out. We'll get L1 over L2 into I1 over I2 whole square. And L1 over L2 is 4 over 1. And I1 over I2 is 1 over 4 whole square. So again we'll get W1 over W2 is equals to 1 over 4. Or you can say W2 over W1 is equals to 4. Okay, so we need to cross verify the options in this case. So option number A, I1 over I2 is 1 by 4. We already calculated here. So 1 is right. Number 1. Second, this is not correct again. Second, W2 over W1 is 4. So this option is also correct. And V1 over V2 is 4:1. So E and V are same. Please keep in mind this is voltage or EMF. So we can say V1 over V2 is just V2 over V1 is just reverse 1 over 4. So in this question A, C and D, 3 options are correct because all these quantities are interrelated. Now next question is, a thin semiconductor of radius r is falling with its plane vertical to the horizontal magnetic field P at position M and Q. Okay. The speed of ring is V. Then the potential difference developed across the ring. So look, ring is moving with velocity V, magnetic field is B, and the effective length, if radius is R, then effective length of this loop will be 2R. Okay. So we can apply first the concept of motional EMF, that is E equals to BVL. Okay. So L is equals to 2VR. So from here we'll get 2R B into B. This is our first point. Okay. Now it is asking which point is at highest potential. So in this case, for highest potential, okay, there is a movement in this direction. So induced quantity will try to apply a force in opposite direction. Okay. According to Lenz's law, any induced quantity tries to oppose the main region behind its induction. Okay. So main region for induction is this loop is falling down. Okay. So the induced quantity will try to apply a force that opposes the motion in this direction. Okay. And we already know that what is the expression for force experienced by a current carrying conductor placed in a magnetic field, that is IL cross B. Okay. So the cross product of length along the current and the magnetic field should be in upward direction. Okay. So if current passes in this direction, okay, so there will be cross product dl cross b, so you need to rotate from L to B. Okay, so from there you will get the direction of current. 1 second, let me figure out. Okay, yes, so if this is the direction of current, then I dl cross B will be in upward direction because V is going down. Okay, so it means current always moves from higher potential to lower potential. Okay, so point Q must be at higher potential. So net EMF is 2RB into V, and Q is at higher potential. Now let's see next question. It is saying an ideal coil of 10 Henry is joined with a series resistance of 5 ohm and a battery of 5 volt is connected. 2 seconds after joining, the current flowing in the circuit in amperes will be. This is very interesting question. Okay. So suppose there is an inductor and it is connected in series with a resistance, and there is a voltage source and switch is just closed. Okay, so if we'll write the expression, this is L, this is R into E. Okay, if we'll write the expression for current, then at this stage you need to remember this one, or by solving the first, let me write the equation so that if you interested, then you can solve it later on. If current I at any instant current I is passing through this circuit, then net EMF, and we apply Kirchhoff's voltage law from here, then E minus L di over dt minus I into R is equals to 0. Okay, so if we'll assume that at initial stage net current is I naught, and we solve this expression, then the solution of this equation is E upon R 1 minus e to power minus R over L into t. Okay. This is solution of this differential equation. But what I would suggest that instead of wasting time in solving differential equation, you can remember the current equation for an LR circuit is I equals to I naught 1 minus e to power minus R over L into T. Okay. Now see, what is I naught? I naught means when switch is just closed. Okay. So when switch is just closed, this inductor does not start charging at very moment. Okay. So this circuit will act as a purely resistive circuit. So this I naught is equals to E upon R at very moment when switch is closed. Okay. After that, this change will take place. So this is the standard equation. So here E and R are given, that R is 5 ohm and E is 5 volt. So E over R is 1. So we can calculate I naught, that is 5 over 5, and it is equals to 1. So we can rewrite our equation, that is 1 into 1 minus e to power R over L. R is 5 and L is 10. So R over L is 2. Okay. So from here we'll get 1 over 2. R over L is 5 over 10. So 1 over 2 into T. And we have to calculate current after 2 seconds. Okay. So put T equals to 2. So from there we'll get I equals to 1 minus e to power minus 1, or you can write 1 minus 1 upon e. But in this question option is given 1 minus e to power minus 1, so we'll go for this option. Option B is right for this question. Now let's see next question. Okay, this is just a very simple question, that what is the SI unit of inductance in Henry. So you just need to recall all the formula related to this. First one, okay, this is watt per ampere. Okay. Second, volt per ampere. Third is joule per ampere square. And fourth is omega. Omega means ohm into second. Okay, so you can check all these values. That energy is equals to half Li square. There is one formula, 1 by 2 Li square. Okay, second is V equals to L delta I over delta T. Okay, third is phi equals to L into I. And fourth is, here we already calculated in previous question, that is R over L into T should be a constant because it was in power of exponential. Okay, so from here you can see that if this unit is constant, then unit of L should be ampere into ohm into second. So this option is right. Here unit of energy is joule. Okay, and L, and this is A square. So from here we'll get joule per ampere square. So this unit is also correct. Next is voltage is equals to inductance into rate of change in current. So this is voltage upon current. So we can consider this option is also right. Okay. But here I have doubt on this question, this option, that V per ampere. Okay. It is, I think, not a correct choice. Volt per ampere is not a correct choice. There must be second also, so we can skip this option. Okay, because V equals to L delta I over delta T. So this is volt second upon ampere. So there must be second also, so this is not right. And second, watt per ampere, it is the correct option. So option A, C and D are correct for SI unit for inductance. Now next question is, a loop of area 0.1 meter square rotates with a speed 60 revolution per second. So area is given, area is 0.1. Okay, speed is given. Speed means it is frequency is given, so we can calculate omega. Omega is equals to 2 pi f, and it is already given in revolution per second, so no need to convert it. So this is 2 pi into 60. Magnetic field is given 0.4 Tesla, and number of turn is given, yes, n is 100. So what is maximum induced EMF? So we already solved this kind of question, that maximum induced EMF is N B A into omega. Okay, so N is 100 and B is 0.4, so we can substitute here. So this is 0.4 into 100 into 0.1, so it would be 4. Okay, I'm directly calculating this. There are 2 point decimals, so it will be eliminated by 100 into 2 pi into 60. Here you can place 2 pi by the pi equals to 3.14. Okay, so after doing proper calculation, we'll get 1507. Okay, so correct answer is 1507 volt. Now let's see next question. This question is for an inductance L and resistance R and battery B, okay, connected with the switch S and are connected in series, right? And two voltmeters are connected. One is VL, another is VR. And when switch S is closed, then what will observe? So let's read the options once so that we can frame our answer. It is saying at initial reading of VL will be greater than VR. The initial reading of VL will be lesser than VR. The initial reading in VL will be the same. The reading of VL will decrease as time increases while the VR will increase to its maximum value. Okay. So to answer this question, let's understand the phenomenon. As we discussed earlier in previous question of the series, that whenever we close the switch, then inductor charging does not start immediately. It takes certain amount of time. Okay. So in the very beginning, it blocks all the current. Okay. It means basically it behaves like an open circuit. So entire voltage will appear across this inductor at very initial point, that is T equals to 0. Plus you can write when we just close the switch. Okay. And as time increases, this capacitor charge, this inductor charging takes place. Okay. And the value of current starts increasing. Okay. And because resistance is connected in series, so the current in this resistance will increase, and according to Ohm's law, V equals to I into R, the voltage across this resistance will increase. Okay. So first thing is, whenever you make switch on, inductor will not start charging, but it will acquire maximum amount of voltage. So VL will be greater than VR. Option 1 is right. And subsequently, when charging process takes place, then current I in the circuit starts increasing. Okay. And the maximum value VL will start decreasing at from an open circuit. It behaves like an ordinary circuit element. Okay, so this voltage VL will start decreasing from its initial value, but current I increases. That's why reading of this resistance will increase until it becomes saturate and maximum value attained by the resistance. So VR is correct. Okay. So whenever we deal with inductors, we must keep in mind that initially it does not charge, so there will be no current in the circuit, and it attains the entire voltage, so voltage will be high. And because there is no current, so its reading will be 0. And when charging starts, then VL decreases and VR increases. So it was all about this paper related to electromagnetic induction and alternating currents. Thank you.